Section: Introduction. In this section, we introduce the concept of reinforcement learning, RL, fine-tuning, which is essential for training language models, LMs, to exhibit desired behaviors and align with human values. This process is particularly relevant in areas such as summarization, conversational agents, and the encoding of social norms. In contemporary applications, RL fine-tuning often involves multiple objectives due to the variety of human preferences, such as the balance between succinctness and detail, or factuality and creativity, as well as the different applications like summarization, coding, and dialogue. Standard RL algorithms typically focus on maximizing a single reward function. To manage the multiple, sometimes conflicting objectives, we often combine these objectives linearly, assigning specific weightings that reflect the importance of each reward. These reward weightings are crucial for the quality of the model and are usually determined through several costly fine-tuning runs. To overcome the limitations of single-objective fine-tuning, SOFT, we explore multi-objective fine-tuning, MOFT, which allows us to create a multi-objective LM. This model can be directed to produce desirable outputs across a range of possible reward weightings without needing retraining. Specifically, during inference, a multi-objective LM takes a desired reward weighting and generates outputs that maximize this combination of rewards, while also adhering to a regularization constraint. A steerable multi-objective LM can serve as an interactive decision support system. Instead of just providing outputs from the best LM chosen by the developer, this system can offer a variety of outputs that cover a broad spectrum of interests, allowing users to select their preferred option. In the realm of LMs, we have examined MOFT through both prompt-based and parameter-based methods. Prompt-based approaches fine-tune an LM by incorporating the reward weightings directly into the prompt. However, we demonstrate through our experiments that this method is not optimal for steerability and can be sensitive to how the weightings are presented in the prompt. On the other hand, the parameter-based approach known as rewarded soups, RS, involves training one LM for each reward function independently and then blending parameters from these separate LMs based on the reward weightings to enable conditional generation during inference. Surprisingly, this zero-shot method can effectively balance multiple rewards by leveraging linear mode connectivity. However, we find that its performance is not optimal for intermediate weightings that were not encountered during training. We propose Conditional Language Policy, CLP, a comprehensive MOFT framework that utilizes parameter space conditioning and multitask training. By applying parameter conditioning from RS, CLP consistently demonstrates greater steerability compared to purely prompt-based methods. Additionally, by fine-tuning on a diverse array of reward weightings, CLP yields higher quality responses than zero-shot methods like RS, while maintaining comparable or superior steerability. We conduct a thorough series of experiments, revealing that CLP outperforms RS and is more steerable than prompt-based MOFT. We observe that CLP retains these advantages across various experimental conditions, including different reward choices and model sizes. Furthermore, we perform an automated evaluation with Gemini 1.0 Ultra, which reinforces our findings that CLP is more steerable and generates higher quality responses than existing baselines. Finally, we present new theoretical insights showing that zero-shot methods can exhibit near-optimal behavior when the optimal policies for individual rewards are aligned, but they fail in other scenarios. In these cases, multitask training, as implemented in CLP, is essential for learning a Pareto optimal policy. In summary, our contributions include the introduction of CLP, a general framework for MOFT that learns multi-objective LMs through multitask learning and efficient parameter averaging. We extensively evaluate CLP in the context of summarization, demonstrating its robust improvements over existing methods in both output quality and steerability across various experimental conditions. We also theoretically establish that zero-shot logit mixing, a specific instance of CLP, is near optimal under certain conditions, and we provide an example where zero-shot methods fail while CLP succeeds. Section Summary. In this section, we introduce Conditional Language Policy, CLP, a framework for multi-objective fine-tuning, MOFT, that enhances the steerability and output quality of language models by allowing them to generate responses based on varying reward weightings without retraining. We demonstrate that CLP outperforms existing methods, such as rewarded soups and prompt-based approaches, by effectively balancing multiple objectives and maintaining high performance across diverse experimental conditions. Section: Conditional Language Policy, CLP. In this section, we introduce the Conditional Language Policy, CLP, framework for MOFT, which allows us to create a variety of algorithms that balance quality, measured by Pareto dominance and steerability, and cost, which relates to the number of parameters used. Essentially, CLP learns a set of parameters that we can use to create a conditioned language model, LM, based on different reward and KL weightings, using a method for averaging parameters that we describe in a later section. Our learning algorithm samples a wide range of weightings to explore its Pareto front across all these weightings at once. This approach involves multitask learning across the spectrum of weightings, directly optimizing the MOFT objective, unlike traditional zero-shot methods. Next, we outline the CLP algorithm, which consists of 3 steps for each training round. First, we sample a prompt and select reward and KL weightings for that round. Second, we condition the CLP on these weightings and generate outputs. Third, we calculate the conditioned objective and update the CLP parameters using policy gradient methods. This final optimization step employs gradient ascent to enhance the objective and can be executed using standard policy gradient techniques like reinforce, PPO, RLOO, or DPO when we have preference data. Now, we describe the mechanism for computing conditional policies. We define an index set for the LM parameters that we want to condition. This index set includes parameters like attention weights, and our choice here affects the steerability and memory cost of CLP. The CLP maintains multiple sets of conditioned parameters indexed by this set, along with one set of unconditioned parameters. To condition the selected parameters based on the weightings, we combine the conditioning parameters with the weightings and then mix this result with a reference set of parameters. Finally, we concatenate the conditioned parameters with the unconditioned ones to form the complete LM parameters. The total number of parameters in CLP is proportional to the size of the index set and the unconditioned parameters. We note that using CLP for inference only requires a single forward pass through the LM, and the parameter averaging is done just once at the start. We can also enhance the prompt with the reward weightings. This approach has been discussed in recent studies and has the benefit of not needing extra parameters, although it does use some of the context and is sensitive to how the information is encoded. We will explore combining parameter space conditioning with prompting in a later section. We also consider 3 different versions of CLP. The choice of index set affects both steerability and memory usage. At one end, we have full CLP, which conditions on all LM parameters, inspired by model soups. At the other end, logit CLP only conditions on the final layer of the LM, which is theoretically sound but less steerable. A balanced option for transformer LMs is ATTN CLP, which conditions on the attention parameters. Our experiments show that ATTN CLP is more efficient in terms of parameters and almost as steerable as full CLP. We emphasize that CLP can be adapted to different LM architectures, and our findings indicate that more expressive parametrizations lead to better performance compared to existing methods like rewarded soups. We also note that the expressiveness of the index set is influenced not only by the number of parameters but also by their positions within the LM. Section Summary. In this section, we introduce the Conditional Language Policy, CLP, framework for MOFT, which allows for a range of algorithms that balance quality and cost by learning parameters that can be conditioned based on varying reward and KL weightings. We describe the training process of CLP, which involves sampling prompts and weightings, generating conditioned outputs, and optimizing parameters through policy gradient methods, while also discussing different instantiations of CLP that vary in steerability and memory usage based on the choice of indexed parameters. Section: Experiments. In this section, we explore several key questions related to our experiments. First, we focus on benchmarking, examining how different methods perform in terms of their effectiveness in expanding the Pareto front and their steerability, which refers to their ability to create content that balances various objectives. Next, we look at ablations to understand how the performance of different approaches changes based on two factors: the number of fine-tuning steps and the size of the model. We also investigate whether parameter space conditioning can be combined with prompting methods. For our automated evaluations, we go beyond just the Pareto fronts. We present evaluations that compare the outputs from our CLP method against baseline models by having Gemini assess the summaries based on their quality and steerability. Regarding our data and models, most of our experiments and ablations utilize the XSUM dataset, which is commonly used for summarization tasks. We initialize our reference policy and reward models from the instruction fine-tuned flawn checkpoints for the T5 model. We primarily use the large model size, which has 770 million parameters, for our reward models, while we mostly use the base model size, with 220 million parameters, for our policies. However, in our model size ablation, we also employ the large size for policies. For optimizing our policy, we use the reinforce method with a control variate, which is a simpler implementation compared to PPO and has proven effective for summarization tasks. We consider three different reward functions. 1. Rouge, which measures how similar the generated summary is to the actual summary. 2. Natural language inference, NLI, a learned model that assesses textual entailment and factual accuracy. And 3. A reward model for summary quality derived from the too long, didn't read, TLDR, dataset. Rouge and the quality model, TLDR, tend to favor longer, more descriptive summaries, while NLI prefers concise summaries, creating a unique tension between these reward pairs in our setup. In our methods, we benchmark three variations of CLP: full CLP, ATTN CLP, and logit CLP. To clarify, full CLP uses one complete language model for each reward, similar to traditional model combinations. ATTN CLP keeps copies of all attention layers, making it more efficient in terms of parameters, and logit CLP only maintains copies of the logit layer, which is theoretically sound but less expressive. For our baselines, we consider A. Rewarded soups, RS, which trains one policy for each reward independently and combines their parameters during inference, representing a zero-shot version of full CLP. B. A prompting baseline that incorporates reward weightings into the prompt and is trained with our multitask objective. And C. In the single reward, multi-KL, setting, we use the recent decoding time realignment, DERA, which maintains two language models, one optimized for a specific reward and the reference model, and combines their outputs. All methods and baselines undergo the same number of training iterations, and we provide additional details and hyperparameters in the appendix. Additionally, we conduct benchmarking experiments with the TLDR dataset to determine if our general findings hold true across different datasets and tasks as we scale up the sizes of our policy and reward models. In our core benchmarking results, we first examine the scenario where we fix a single reward function and adjust the KL regularizer to test the trade-off between KL and reward. We use a combined reward that gives 90% weight to the NLI reward and 10% to the Rouge reward to prevent exploiting the NLI model. Our findings indicate that all methods, except for logit CLP, can effectively balance reward and KL, allowing for a smooth transition from the reference policy to a fully fine-tuned model. This suggests that our parameter mixing approach, trained with a multitask objective, is competitive with the state-of-the-art DERA method for managing the reward-KL trade-off. Furthermore, we observe that our CLP method is approximately twice as computationally efficient as DERA during inference, as DERA requires two model calls for each token. Thus, the speed of inference is a significant advantage of parameter mixing over logit ensembling. Section Summary. In this section, we evaluate various methods for summarization using the XSUM dataset, focusing on their performance, steerability, and the impact of model size and fine-tuning steps. Our experiments reveal that most methods can effectively balance reward and KL divergence, with our parameter mixing approach demonstrating superior computational efficiency compared to the state-of-the-art DARA method. Section 2 Rewards, Fixed KL Regularizer. In this section, we explore a scenario involving two rewards with a fixed KL regularizer to examine the balance between these rewards. We present the Pareto curves for two comparisons, NLI versus Rouge and NLI versus TLDR. The axes represent the KL regularized rewards, where the x-axis corresponds to the value of the first reward and the y-axis corresponds to the value of the second reward. This reflects the true objective we aim to maximize through fine-tuning. Our findings indicate that both CLP and prompting significantly outperform the baseline RS, highlighting the advantages of multitask training over the zero-shot approach of RS. We observe that full CLP and ATTN CLP display Pareto fronts that are more manageable and evenly distributed compared to logit CLP and prompting, which tend to show a mode-collapsed behavior. Notably, while ATTN-CLP efficiently replicates only the attention weights, it still surpasses the baseline RS while maintaining well-structured Pareto curves. Therefore, ATTN-CLP strikes the best balance between steerability and the number of parameters used. For more results, we refer to the appendix. Next, we investigate a 3-reward setting to assess the trade-offs among all reward functions. We plot the KL regularized value, normalized against RS, for 13 different reward weightings. At the extreme weightings, where each weight corresponds to one of the rewards, RS behaves like single objective fine-tuning and naturally outperforms CLP in prompting, as expected. However, at intermediate weightings, where the weights are not equal to the extreme values, full CLP consistently outperforms RS. We find that ATTN-CLP remains competitive with full CLP while using only 20% of the memory overhead. Similar to the 2-reward scenario, ATTN-CLP achieves the best trade-off regarding steerability and parameter count. Additional results for the 3-reward setting can be found in the appendix. In summary of our core benchmarking results, we find that multitask training allows CLP to surpass the zero-shot RS baseline. Importantly, both full CLP and ATTN-CLP maintain a well-structured Pareto front that is more spread out than that of logit CLP and the prompting baseline. Overall, ATTN-CLP offers a favorable trade-off in terms of Pareto front and steerability while utilizing fewer parameters than existing methods. We also examine the effect of training iterations. Our analysis shows the evolution of Pareto curves over 90,000 training steps for CLP instances. Both full CLP and ATTN-CLP become steerable after just 10,000 steps, while prompting only achieves steerability at 60,000 steps. Logit CLP shows a similar trend, being less steerable in the earlier training stages. Additionally, the optimization process for full CLP and ATTN-CLP is much smoother compared to prompting and logit CLP. Complete results are available in the appendix. Furthermore, we analyze CLP with prompt conditioning. The Pareto fronts for full CLP, the prompting baseline, and full CLP with prompting are presented. For the comparison of NLI versus Rouge, full CLP with prompting shows a slight improvement in steerability, while there is minimal difference for NLI versus TLDR. Thus, prompt conditioning does not negatively impact performance and can be slightly advantageous. More results can be found in the appendix. Lastly, we rerun our experiments using T5 small and T5 large models to see how our findings vary with different model sizes. The Pareto fronts for NLI versus TLDR reveal that full CLP and ATTN-CLP continue to robustly outperform the RS baseline and maintain steerable fronts. Interestingly, prompting collapses to a single point for the T5 small model but shows better distribution for the T5 large model, indicating that prompting is sensitive to model size and that a larger model can enhance its steerability. We provide results for other reward pairs in the appendix. In summary of our ablation studies, while combining prompting with CLP did not significantly enhance steerability, prompting may show improved steerability with larger models or extended training time. Across various settings, full CLP and ATTN-CLP consistently demonstrate superior performance and steerability, suggesting they are robust conditioning architectures for multi-objective fine-tuning when paired with multitask training. Section Summary. In this section, we explore the performance of multitask training using 2 and 3 reward settings with a fixed KL regularizer, demonstrating that both full CLP and ATTN-CLP significantly outperform the zero-shot RS baseline while maintaining a more steerable Pareto front. We also find that ATTN-CLP achieves an optimal balance between steerability and parameter efficiency, and that our results remain consistent across different model sizes and training iterations. Section: Automated Evaluation. In this section, we conduct an automated evaluation to determine whether the improved Pareto fronts from CLP lead to better generations compared to our baseline methods, which include prompting and rewarded soups. We set up our evaluation using the NLI versus TLDR framework with T5 large models, as discussed earlier, and we analyze 2,000 articles from the XSUM validation set. For this purpose, we employ Gemini 1.0 Ultra as our automated evaluator to assess the summaries generated by CLP instances against each baseline, focusing on their conciseness and overall quality. Specifically, for each article, we generate summaries from both CLP and a baseline using different weightings. For high NLI, we use a weighting of 0.8 for NLI and 0.2 for TLDR, and for high TLDR, we reverse these weightings. We then ask the automated evaluator to determine which summary is more concise or of higher quality. To avoid any bias from the order of comparisons, we alternate the order of the evaluations and consider a comparison consistent if both orders yield the same result. We refer to the appendix for more details on the automated evaluation process. For each article, we declare an algorithm the winner, meaning it is more steerable, if the evaluator prefers its summary in both comparisons or if it is preferred in one comparison while being inconsistent in the other. If neither algorithm wins, we label it a tie. With this evaluation framework, we present the win rates of different CLP variants against the two baselines. Our findings indicate that full CLP and ATTN-CLP show improvements of 11.6% and 16.5% in win rates compared to the multitask-trained prompting baseline, and 4.9% and 9.5% over rewarded soups. Logit CLP performs similarly to prompting but is less effective than rewarded soups, showing a decrease in win rate by 3.1%. Notably, ATTN-CLP and full CLP achieve the highest win rates relative to both baselines in this automated evaluation, with ATTN-CLP also being more efficient in terms of parameters. Overall, our automated evaluation aligns with previous Pareto front results and confirms that CLP generates higher quality multi-objective language models with better steerability, both quantitatively and qualitatively. Next, we scale up CLP by increasing the size of both the policy and reward models while performing multi-reward fine-tuning on the TLDR dataset. We train 2 reward models using T5XXL, which has 11 billion parameters, one for factuality, referred to as NLI, and another for summary quality, called TLDR. We follow the same training procedure for the reward models as before. For our policy model, we utilize T5XL, which has 3 billion parameters and is initialized from the Flan checkpoint, training all methods for 6,000 steps while keeping other configurations consistent with our previous 2 reward experiments on XSUM. We repeat this experiment across 3 different sampling distributions and present the results. Our observations reveal that both ATTN-CLP and full CLP significantly outperform the baselines while maintaining smooth steerability in their performance curves. In contrast, logit-CLP appears to be limited in its effectiveness, likely due to a representational bottleneck. We also notice that the steerability of the learned policy may improve as the weight sampling distribution narrows, although this could lead to a decrease in Pareto optimality. Importantly, we have seen this trend consistently across various model sizes, datasets, and sampling distributions, reinforcing the robustness and reliability of CLP for multi-objective fine-tuning. In terms of related works, we categorize approaches for multi-reward alignment, or MOFT, into 2 main types: prompt-based and parameter-based conditioning. Prompt-based methods include personalized SOUPs, which use custom prompts to tailor language models based on binary weights for different rewards; CPO, which integrates prompting within a DPO framework; and RIC and DPA, which utilize prompting in a supervised fine-tuning context, differing from our focus on reinforcement learning fine-tuning. On the parameter conditioning side, Rewarded SOUPs offers a zero-shot method for multi-reward alignment by averaging parameters at inference time for language models trained independently to optimize each reward. A recent study introduced a method where reward weightings are embedded as singular values within the Adalora framework, which can be seen as an application of our proposed CLP framework. Regarding KL realignment, decoding time realignment, DERA, mixes logits between a reference model and another language model learned through SOFT, using a minimum KL weight. A recent paper demonstrated that this approach is effective for balancing multiple rewards. Additionally, techniques like model souping, learning policy subspaces, and objective weight conditioning have been applied in areas beyond language models. We leverage these advancements, along with multitask training, to create steerable language models during inference. Section Summary. In this section, we conduct an automated evaluation to compare the generation quality and steerability of our CLP models against baseline methods using a dataset of 2,000 articles, finding that full CLP and ATTN-CLP significantly outperform the baselines in terms of summary quality and conciseness. Additionally, we explore scaling up CLP with larger models, confirming that ATTN-CLP and full CLP maintain superior performance and steerability across various configurations, reinforcing the robustness of our approach for multi-objective fine-tuning. Section: Theory for Logit Mixing and CLP. In this section, we conduct a sensitivity analysis for logit mixing, which is a zero-shot method for multi-objective fine-tuning, MOFT, and we derive regret bounds for its Pareto front. Although CLP employs parameter mixing instead of logit mixing, we find this analysis valuable because of the similarities between parameter and ensemble mixing. For our sensitivity analysis, we concentrate on a simplified scenario called the 2-reward, fixed alpha setting, but our findings can be applied to more general cases. We define a variable, lambda, that ranges from 0 to 1, and we let zeta_lambda represent the logits of the optimal policy, denoted as pi star, for specific weightings of W, which are 1 minus lambda, lambda. Through the analytical solution of KL regularized reward maximization, we observe that the optimal logits at lambda can be expressed as a mixture of the optimal logits for each individual reward. Specifically, zeta_lambda equals 1 minus lambda times zeta_0 plus lambda times zeta_1. This means that if we have the optimal policies for rewards R_1 and R_2, logit mixing allows us to compute the optimal policy for any intermediate lambda without needing additional information. However, in real-world scenarios, we typically do not have access to optimal policies. Instead, we only have approximations that are epsilon close to optimal. Therefore, it is crucial for us to understand how sensitive logit mixing is to these approximations. We establish a bound on the suboptimality of logit mixing in relation to epsilon and a concentrability coefficient, which measures how well the policies cover each other. This coefficient is defined as the maximum ratio of the probabilities of one policy given an action to the other policy given the same action. We state Theorem 1. If pi_1 and pi_2 are epsilon optimal policies for the single objective fine-tuning with rewards r_1 and r_2, respectively, then for any lambda between 0 and 1, the logit mixture of pi_1 and pi_2, denoted as pi_lambda, has its suboptimality bounded by a certain expression involving p_min, which is the minimum probability of pi_1 and pi_2 across all relevant input-output pairs. The proof of this theorem can be found in the appendix. However, we note that the coverage terms can become infinite if the policies pi_1 and pi_2 do not adequately cover each other. A zero-shot method will be robust to approximations when the expert policies for each individual reward overlap sufficiently. Yet, as we will demonstrate next, zero-shot approaches can fail when this coverage condition is not met. To illustrate this, we present a counterexample for zero-shot MOFT. Logit mixing is limited in that it can only combine behaviors from the two extremes, meaning that if an intermediate weighting requires a new behavior, logit mixing will not succeed. We consider a simple scenario with one context and three possible outputs: y_1, y_2, and y_3, with rewards defined as r_1, x dot equal to 1, 0, 0.75, and r_2, x dot equal to 0, 1, 0.75. The optimal policies for r_1 and r_2, when alpha equals 0, are pi*_1, x equal to 1, 0, 0, and pi*_2, x equal to 0, 1, 0. However, the optimal policy for a lambda of 0.5 is 0, 0, 1, which represents a qualitatively new behavior that cannot be achieved through zero-shot logit mixing, highlighting a failure case for this method. In the appendix, we provide a figure that shows how the random sampling baseline, which is a zero-shot approach, fails to learn the Pareto optimal policy in this example, while CLP, which utilizes multitask training, succeeds.